Okay, another day, another past paper. I just recovered from breakthrough COVID. Didn't have it too bad, but I am so happy I had access to those vaccines. Thornley lives to fight another day. Alrighty, question. So the average was 18.5 out of 30. There's the grade boundaries. Question 1. Balance the equation. So everyone has their own way of doing it, but for me, I try to leave the simplest thing till last, and then I'll just fix it with a fraction if I need to. So the simplest thing looks to be just the oxygen, so I'll leave that one till last. There's got to be an 8 there, isn't there? Because of the 8 here. And there's got to be a 9 there to balance the hydrogens. Now I'm going to fix the oxygen. So on this side, I've got 17 oxygens, okay? So that would mean I would need 17 over 2 there, wouldn't it? Now the answer wants integers. So how am I going to fix this? Well, if I just double every number, that should give me integers, shouldn't it? So this becomes 2. That just becomes 17. That becomes 16. And that becomes 18. So what have I got? I've got to sum them all up. So 19, 29, 39, 49. Is that 53? So C. 1 is C. Yep. We're on our way. Ooh, that's a nasty looking Avogadro's. How many moles of oxygen atoms? So if I've got half a mole of that molecule, for every, well, let's have a think. For every 1 mole of this, let's do 1 mole, how many oxygens have I got? Well, I've got 4 here. Actually, I've got 8. So there's 8 there and 6 there. So that gives me, for every 1 mole of this molecule, I'm going to have 14 moles of oxygen. Well, they're actually asking me for half a mole. So that's going to be 7 moles of oxygen, isn't it? 7.00. So 2 is B. Yep, 2 is B. So the trick really with these is you take the number of moles given and you multiply it by the number of atoms in the molecule that you're interested in this case, oxygen. Okay, question 3. So I'm going to do the boxes method. Moles, mass, molar mass. The molar mass of calcium carbonate is 100. Never worked that out. I've got to work out how many moles of carbon dioxide I've got. After all, if I end up with having 1 mole of carbon dioxide, that's going to be 22.7 decimeters cubed, because it says 22.7 decimeters cubed is 1 mole. So let's see how many moles I've got. I think this is an excess and limiting question. They've not actually said that. So I've got 1 gram here, and so moles is mass over molar mass, so that's going to be 1 over 100. For hydrochloric acid, moles is concentration times volume. Concentration is 2, and the volume is 0.02, because I converted that 20 to decimeters cubed. So that's going to come out at, that's going to be 4 over 100. Now you can tell it's excess and limiting, because 1 is to 1 over 100, as 2 is to 4 over 100. That ratio doesn't work. Something's gone wrong. The boxes aren't working. So it's excess and limiting. Got too much of one chemical, not enough of another. So how would you work it out? Well, you can probably see that there's too much hydrochloric acid here, but this is how you do it if the numbers are more confusing. So I would just say 1 over 100 and then 4 over 100 here. Divide that by the coefficient, which is 1, and divide that by the coefficient, which is 2. Lowest is limiting, so whichever's lower is limiting. And so it seems clear to me that the calcium carbonate has a lower number, so that's limiting. That's the one that runs out first. So hydrochloric acid is in excess. There's too much of it, too much of it. All right, so then I know now that 1 is to 1 over 100, as 1 is to 1 over 100. Okay, that's my minute and a half. But we've not finished the question, but that's how much time we budgeted. If the question asked how many moles of carbon dioxide, that's my answer. But it wants to know the volume. Well, I happen to know that 1 mole is 22.7 decimeters cubed. It's in the question. And I've got 1/100th of a mole, and I want to know the volume of that. So that's going to be, so that's the unknown x, my volume. So 1x is 1/100 times 22.7, and that is C. Yeah, 3C. Let's hope some of the other questions are a bit quicker. Question 4. What affects the molar volume of an ideal gas? So the molar volume of an ideal gas. So 1 mole of any gas at STP is 22.7 decimeters cubed. So does the pressure matter? Yeah, because it has to be at standard temperature and pressure. So the pressure matters. Does the temperature matter? Yeah, I mean, it's written there, STP. And how would you know that? Well, it's actually in the question above, isn't it? The molar volume of a gas. Cancel that last bit. And the empirical formula of the gas, does it matter if... No, because it's any gas, isn't it? It doesn't matter what gas it is. It's any gas. So I think that only 1 and 2 matter, and that's A. 4A. Correct. Wow, I should do this for a living. Question 5. What's going on here? Alrighty, so the atomic number's 12, so 12 protons. The difference in a number is the number of neutrons, and so that's going to be 12. And magnesium normally comes with 12 electrons, but it's lost a couple of them because it's 2+. So it's only got 10 electrons. An iron with 12 protons. Okay, so that's C, isn't it? 5 is C. Okay, some faster questions there. Line spectrum. I like that. I think big jump is big energy. Big jump is big energy. And if you're releasing light, you've got to be jumping down. So big jump is big energy. And if you're releasing light, the electron's jumping from a higher to a lower energy level. The IB also wants you to know if it jumps down to n equals 1, it's UV. N equals 2 is visible. N equals 3 is infrared. So with that, what's the question? The longest wavelength of light. So if it emits radiation, if it emits light, it must be jumping down. So this one's wrong, and this one's wrong. So that leaves me with just A and C. The longest wavelength is the lowest energy. So you know, big jump, big energy, and anything with so big jump is big energy. That's how I think about it. And big energy is a big or a high frequency, isn't it? It's going to be high frequency, which is going to be the shortest wavelength. Well, they want the longest wavelength. So that's the smallest energy. The smallest jump down, well, that's going to be C, isn't it? The smallest jump down is C. 6 is C. 7, what increases down group 1? Oh, plenty of things. They get bigger, because every time you go down a main energy level, you're adding a shell. There's more electrons, there's more protons, there's more neutrons. Let's have a look. So what increases down group 1? Well, there we go, atomic radius. Yeah. As you go down group 1, you're adding shells, and they get bigger and bigger and bigger. So 7's A. Wasn't too bad. 8. What element is a lanthanide? Well, looking at their periodic table, you can see that the lanthanides are this group here, this row, sorry, because the actinides are that one. So HF, TB, U and Y. Wow, that's some element blindness there. So TB, so 8 is B. I told you, I'm just coming off the old COVID. Brain's slowly coming back online again. So 8's B. 9. Urea molecule. The urea molecule was the first ever organic chemical synthesized not from nature. Initially, people thought you could only get organic chemicals from nature, and then some guy got some white powders, artificial stuff, mixed it up and made that. That's quite revolutionary, thinking that you can only make chemicals from life, and this guy made it from stuff that wasn't alive. How many bonding electrons? Well, the bonding electrons are in the bonds, aren't they? I see 1, 2, 3, 4, 5, 6, 7. I see 8 bonding electron pairs, and each pair has 2. So isn't that 16? 8 bonds times 2 electrons per bond is 16. So that's going to be B, 9B. I don't understand what they were trying. Maybe they were thinking that you'd put in the lone pairs here and then get confused with that, or I think that one's quite easy. Question 10. So why does water have a higher boiling point than hydrogen sulfide? So let's have a look. Water is H2O, and hydrogen sulfide, which is the eggy smell in farts, it's actually about as toxic as cyanide. So why don't farts kill you? Maybe yours do. Because it's super, super smelly. You're super attuned to that smell. So H2S, you might naively think it's got more electrons, more London dispersion forces. But no. It's hydrogen bonding, isn't it? It's hydrogen bonding. So the reason that water molecules stick together more than hydrogen sulfide molecules is that water has hydrogen bonding. So anything with hydrogen attached to oxygen, hydrogen attached to fluorine, hydrogen attached to nitrogen has hydrogen bonding. This is not a hydrogen bond. That's a covalent bond. Hydrogen bond is an intermolecular. It's between the molecules. So this is a hydrogen bond. That is basically what's holding you together. If I pressed a button and removed all the hydrogen bonds in your body, you just flop down, squidgy. Question 11. Silicon dioxide. So, gentlemen, if you ever decide you want pectoral implants or calf implants, and don't ask for silicon implants. Silicon is hard like a rock. Silicone is squidgy. And this actually is silicon dioxide. That's sand. Subtly different. So I got the picture off the internet there. It's a giant molecule. You'd actually have to learn how to draw this. So it's a giant molecule. And the bond angles, well, it's based on the tetrahedron, isn't it? So that's 109.5. So what's that going to be? Best answer is B, 11B. Next. Question 12. Which metal has the strongest metallic bond? So lithium's quite tiny. And rubidium, which burns with a ruby flame, it's quite big. Each of them drop 3 electrons into the sea if there's 3 ions formed. Well, they're both +1, so it seems naively that you might think that the bond's going to be the same strength because each ion is +1. But it's to do with charge density. This +1 in the lithium is concentrated into a nasty, tiny little ion. And so it behaves much more attractively than the +1 in the rubidium. Charge density. If I was to pull an electron off of my head would now be positive, but it's certainly not that attractive because one tiny positive charge spread out over my enormous, bald but very symmetrical head wouldn't make it very attractive. But something super tiny like an atom, you pull an electron off and now it's very, very positive. So lithium has the highest, has the strongest metallic bond. So that's going to be 12A. Also, maybe you remember your teacher, remember her throwing lithium, potassium and sodium into water. Lithium's really hard to cut. compared to the others. Strong metallic bonds. And my nightmare is that I'm gassing on about science, and as I cut it, it's like cutting a pickled onion. The damn thing shoots off, goes into my mouth, fizzy bang. Question 13. What can be deduced from this? So I'll put that in there. Oh man. So that's exothermic, isn't it? Exo, that's hot. And the other one would be endothermic, would be that one. So endo, I think of that as cold. 3 letters, 4 letters. True story. That's absolutely true. One of the kids in the last school told me that they remember that exo is hot because they both have an O in it. The more you think about that, the more you think what a bad teacher I must have been. Anyway, so if it's got low energy, it's stable. And if it's got high energy, it's unstable. That makes sense, doesn't it? This has high energy, and now, bollocks. And now it has low energy, potential energy if you want. So anything with a low energy is more stable. This is more stable. This is less stable. Okay. So the reactants are more reactants are less stable than the product, and it's exothermic. So it's A, isn't it? 13A. Yep, 13A. The IB wants you to know 2 reactions that are exothermic: combustion, which is burning stuff, and neutralization, acid base. 14. Oh, I'm not looked to the answer yet, but my intuition, such as it is that it's average bond energies, and so the average bond energies are an average. They're all gases. I thought that was going to be the trick, because average bond enthalpy only works for gases, but they are all gases. So I'm going to say 14B. Yeah, 14B. It's an average. 14C is true. 14D is true, but it's not the right answer. 15. What can be deduced? Ozone. Blah, blah, blah. Okay, so we've got ozone, which is actually a 1.5 bond, isn't it? There, that's ozone. And then is it regular oxygen, which is a double bond? Princeton. Well, so what's the stronger bond? The stronger bond's going to be the double bond, isn't it? So that's going to need higher energy to break it. It's going to need higher energy to break this one. It is, after all, a stronger bond. And if it's going to need a higher energy, then that means it's also going to need a higher frequency. But it's also going to mean it needs a shorter wavelength. Now, is that enough? So the bond between atoms in molecular oxygen is a double bond, so that's true. The bonds in ozone are delocalized, that's true. The bonds in ozone are stronger than oxygen, so C is wrong. And D, the bonds between atoms in molecular oxygen need more energy to break. So A, B, and D are right. Well, let's see what the question is. Yeah, it's D, isn't it? Yeah, 15D. That's interesting. They're giving you a whole bunch of true statements, again, but they don't answer the question, but they are true. Alrighty. Chalk and hydrochloric acid. What doesn't make it go faster? Well, if I make the chalk smaller, it does go faster, doesn't it? Oh, first of all, check where the excess is. See which is what is there too much of. And there's excess hydrochloric acid. So if I made the chalk smaller, that would make it go faster. So A's wrong. B, if I made it hotter, that would make it go faster. More collisions per unit time and more energy per collision. Increase the concentration of hydrochloric acid. Yeah. More concentrated acid reacts faster. Increase the volume. Yeah, okay. So if I've got too much hydrochloric acid, let's say I've got like a litre of it, and that's way too much. If I put in 2 litres of it, it's still way too much. It's not going to make the reaction any faster. So the answer is D. I don't know if that's true in real life, but it's true in IB world, which is the world you and I live in. 16D. What was that like? Yeah. 17. How can I monitor the reaction? Alrighty. Plenty of ways you can monitor reactions. Conductivity. You're making ions and removing ions. I bet the conductivity changes. I bet the pH changes because I'm getting rid of acid. There's gas coming off. I could measure the volume of gas at a constant pressure and temperature. I could measure the temperature of gas at a constant volume and pressure, or I could measure the other way. Yeah, there's a bunch of stuff you could do. But everything here is white or colourless. So probably not going to use a colorimeter. Alrighty. Change the colour of the reaction mixture. So I is wrong. Everything's white and colourless, and it's all bubbly, and it's all just going to be a disaster. There isn't a nice colour change there. Change in mass. Yeah, it should get lighter, shouldn't it? As gas is produced, the gas is going to blow away, and it should get lighter. Changing the volume of the gas. Yeah, I'm making more gas. At the beginning, I've got nothing, and at the end, I've got something. I'm just going to check to see if the container's open. Sometimes they try and do that. If the container's closed, you're not going to lose the gas. No, they're not messing us about. So it's 2 and 3, which is C, 17C. Nice. 18. KC. This was the easiest question on the paper, almost certainly. Everyone can do this. So it's products over reactants, isn't it? Products over reactants. And then you've got to raise the coefficient there to make it that power. So that gives me ammonia squared and oxygen squared, and everything's multiplied. But I bet they're going to try and add it. Oh no. All right then, what's going on? That D? Yeah, 18D. No problem. I taught equilibrium for about 15 years and I didn't understand it at all. No one knew I didn't understand it, and I could still get you a 7 in it, but I didn't really understand it. I think I understand it now. Which of the following does not react with dilute hydrochloric acid? Okay, so there are 5 things that react with acids. You've got reactive metals, carbonates, hydrogen carbonates, hydroxides, and oxides. All right then. So I see A is a carbonate, so it ain't A. Oh no, do not react. Yeah, it's not A. I see copper is a metal. We'll put a pin in that and decide if it's a reactive metal, then it will react, or an unreactive metal, then it won't react. C is another metal, and D is an oxide. So metal oxides react. All right. So B and C. Now, acids are based on hydrogen. And so copper is below hydrogen. It ain't going to react with a regular acid. And zinc is above hydrogen. It's more reactive than acids. So which one does not react? That's going to be the copper, isn't it? Because it's below the hydrogen. Anything below hydrogen won't react with acids. Alrighty, so that's 19B. Got them all right so far. 20, which of the following is correct? So a weak acid is a proton donor. Yep, so let's choose methanoic acid. I sat on a horsefly in Mexico and it stung me on the bum with methanoic acid. Otherwise that would just be a weird thing to mention. It was really painful, much more painful than I thought. So methanoic acid, it partially dissociates, not fully dissociates, I don't know, maybe 1 in 50 of the methanoic acid molecules break apart. So a weak acid, it's a proton donor, yeah, that's a proton. And it doesn't conduct electricity. Aqueous solution shows good conductivity. No. For conductivity, you need freely moving charged particles. And there's not that many freely moving charged particles because most of the methanoic acid stays together, doesn't break apart. So it's B, isn't it? 20B. Nice. Okay, 21. What's reduced? Let's have a think then. Elements have an oxidation state of 0. Oxygen's -2 in a compound. You don't have to write them all out. You can just write one out. But don't add them up. If you were to, this is good, -2 or 7 -2s. But if you were to write -14, no, that's wrong. Lovely. -2 plus 1 plus 1, that's -2, that's +3. All right, so this ammonium dichromate reactant, hopefully you know that NH4 is plus, which would mean that ammonia must be -3. Sorry, nitrogen must be -3. Is that right? Yeah. So that's -3 plus 1. Doing some maths here, that's +6 and +6. Okay, what oxidation state's gone down? It's the chromium, isn't it? It's gone from 6, it's reduction, to 3. That's why it's called reduction. The oxidation state goes down. So that's C, 21C. Nice. 22, which is not redox, so the oxidation states don't change. Neutralization isn't redox. The oxidation states don't change. So whatever's acid base, it's that one. That's the last one. That's D. I don't even have to work my way through it. 22 is D. Yeah, 22 is neutralization. It's not redox. Ethanoic acid, sodium hydroxide. What happens at the positive electrode with molten strontium bromide? Alrighty. So strontium bromide, you've got 2 ions. You've got strontium plus and bromide ions. So at the positive electrode, the bromide ions are going to go due to electrostatic attraction. Negative ions attract the positive electrode. And in IB chemistry, you always make, in SL, you always make the element. So the bromide is going to turn into bromine. Okay, so I'll just balance that then. 2 of those there, and I've lost a couple of electrons there. Right, what the hell's the question? Formation of bromine, yeah, so it's going to be A or B. Always make the element in SL. And oxidation is loss reduction. It's oxidation, isn't it? So formation of bromine oxidation, 23A. Nice. Okay, 24, what's going on here? I don't like this whole functional group, and I don't even know what the name of it is. I don't like that. So to me, this is an alcohol group. But the IB says that, okay, this is a hydroxyl group. Oh, don't mess me about. It's an alcohol, isn't it? Anything with a hexagon, the benzene, is called an aromatic because it smells. They all smell. That doesn't make any sense to me. This here is actually a carbonyl group. But if it's attached to this nitrogen here, it's an amide group, which is not IB chemistry anymore, SL. This cheeky thing here is an alkyl group. It's methyl. Alkyl is methyl. So what's going on? Carboxyl, no. So A is wrong. Carboxyl is this, like a carboxylic acid. So A is wrong. B is amino. Amino is a nitrogen with some stuff coming off. So it can't be that nitrogen because it's got that's an amide group, this kind of thing here, and that's beyond IB. I think that's a bit cheeky to put this. Nitrile is cyanide. I'm not even sure that's on the syllabus. But, so the answer is D. It's hydroxyl. D is the answer. Is it? 24D. Oh, I didn't like that one. 25. What describes a reaction between a halogen and ethane? Oh, isn't that initiation, propagation, termination? So that's where you had the chlorine at the beginning and you zapped it with UV light. And and then you've got a homolytic fission. So it's free radicals. I heard in the old days, what a teacher would do is they'd get a bag of chlorine and ethane together in a dark room. Oh, nearly my bedtime. And you go in as a chemistry student, and there'd be these bags on the table, and then they'd give you these cameras, the old ones that were portable, and they'd have a flash and a film. And as you took a photograph of it, the UV that came out of the flash bulb would detonate the chlorine and the ethane and explode as the photograph went off. And there's these magnificent pictures of people going, oh! Can't do that anymore. Mostly because the chemicals that are produced aren't good ones, those halogenated alkanes. All right, so we did it. So it's free radical and it's homolytic fission, isn't it? So it's 25A, yeah. So if it's a homolytic fission, homo means that you produce the same thing. In this case, two free radicals, the same thing. If I produced chlorine plus and chlorine minus, that would be different things. So that would be heterolytic. Lysis is cut in Greek, I think. How do I convert ethanol into ethanol? I remember my first explosion. I put in the orange acidified dichromate with the alcohol. I heated it up, it exploded, it turned green as it made chromium 3+, and the room smelled of alcohol and the terrible smell of wee when you have a wee in the morning after you're hungover. That's ethanol, terrible, and vinegar. Oh, I had to evacuate the classroom. So what am I doing? Ethanol to ethanol. I need oxidizing agent. Now it goes ethanol, ethanol, ethanoic acid. So I don't need a lot of oxidizing agent. I just want to go from ethanol to ethanol. So I need excess ethanol. So it's going to be C or D. And I want to take my chemicals off before it finishes. And so that's reflux or distillation. Distillation, 26D. Oh, that's a tricky one. So distillation allows you to remove the chemical ethanol before it cooks itself up to ethanoic acid. But there we go. 27. What has a secondary carbon atom? So secondary, I'll do the simplest one that it could be. The simplest one it could be would be this. So that's secondary because the rule is it halogens? Yeah. So find the halogen, find the carbon it's attached to. How many are directly attached to that? How many carbons are directly attached? There are 2. That's secondary. So we have to look through these here. So it seems plain to me that it's this one, isn't it? The first one. Find the halogen, find the carbon it's attached to. How many directly attached to that? 2. So 27 is going to be A. Yep, 27A. 28, home stretch. So infrared, well, infrared tells you what bonds are there. Is it OH? Is it CH? Is it HBr? What's going on? So it tells you the bonds. Yep, so 28 is C. For completeness, mass spectroscopy is where you snip the molecules up, molecular iron, all of that business. X-rays tells you about the distance atoms or ions are apart in a crystal, and H1 NMR, clues in the name, tells you about the hydrogens. 29. So H1 NMR, alrighty. So it can tell you about the hydrogen environments and the ratio of hydrogens in that environment. There's only one peak, so there's only one hydrogen environment. If there was 2 peaks, there'd be 2 hydrogen environments. So that's what I know about that. There's only one hydrogen atom? No. Something like methane would give you only one peak. Each of the hydrogens is in the same environment. So just because there's one peak doesn't mean there's one atom. It just means that there's one hydrogen environment, which is B, 29B. Oh my God, I'm going to get 30 out of 30. And the last one, I'm not even going to look at the question. No, I am, because I thought they were going to do PV, which is their favourite one. Which of these represents N and T in an ideal gas? PV equals nRT. Okay, focus on me for the 30. PV equals nRT. So I want N and T. So PV over T equals nR, which gives me 1 over T is proportional to N. All right then. Don't mess it up. So 1 over T is proportional to N. So which graph is that? As N goes up, T goes down. So it can't be that one, because they both go up. This one doesn't make any sense because you'll actually hit the axis. You're never going to hit the axis there. For this one here, one goes up, the other goes up, but one goes up, one goes down. It's D, isn't it? 30 out of 30 is my job though.